So this video is actually a pre-lab. So what we are going to be doing next class is a lab called the Scooter Friction Pre-Lab. And in that lab, you guys are going to be riding the scooters that we've been keeping around in our class for so long. And you're going to actually use these scooters to determine something called the coefficient of friction. Coefficient of friction. So I want to explain what the coefficient of friction actually is. And the symbol that we use for the coefficient of friction is actually this Greek letter mu. So it looks kind of like an M. So it's like if we're writing it, remember in elementary school where you had like the little lines and like your capital letters had to go all the way to the solid line and your lowercase went to the middle. So a mu would be written like this. So that's a mu. And what mu means as the coefficient of friction is the ratio between the frictional force on an object and the normal force on an object. So it is the frictional force divided by the normal force. Now let's take a look at an example. So here's an example of an object that is being pushed across a surface. So here's our lovely object, and it's being pushed across this surface by my little green person. Now, let me identify the forces that are acting on this object. So I'm going to draw a free body diagram. My object is being represented by this yellow dot here in the middle. So we always know that the force of gravity is acting on our object, and that is Fg. And the force of gravity means the weight of the object. And when we multiply mass times the acceleration due to gravity, we get the object's weight in newtons, which is our SI unit of force. Okay, another force that is acting on this object, well, we can see that it's sitting on a surface, and if we can assume that that floor is pretty solid and that the block isn't falling through the floor and the floor isn't springy and pushing it up into the air, then we should have a normal force that is equal in magnitude and opposite in direction of our force due to gravity, right? So our normal force here should be equal in size and opposite in direction to our weight, Fg. So those should be balanced, which means that if we think about the sum of the forces in the y direction here, that should equal 0 newtons. Those should be in equilibrium. So we would say the sum of the forces in the y direction are equal to our normal force plus our force due to gravity, and those added together are equal to 0 newtons. And then if I solve this for Fn, you can see that we would subtract Fg from both sides, which is where you would get that relationship that Fn is equal to negative Fg. So I'm just basically taking this equation here and solving it for Fn. And that's how we know that the sum of the forces here, that these are balanced, because the sum of the forces have to equal 0. Okay, now let's take a look at the forces that are happening in the x direction. So we can see that I'm applying a force. So I'm going to put an arrow here, and I'm going to label this F applied, or F app. And in some cases, we just had the force applied acting on something, and a lot of times there was a frictionless surface, so no friction was acting on it. Well, now we're definitely going to have friction acting on these things. And so that friction is actually caused by the surface. And it's a force from the surface that's acting backwards against the direction of the applied force. And I'm going to label that capital F with a nice little curly lowercase kind of cursive looking italicized F. And as I was saying, that force is determined by the surface here. So it's partly determined by how much the surface has to push up on the object. So heavier objects are going to have a greater normal force supporting them. So that makes them a lot harder to move. Also, the roughness of this surface determines how hard it's going to be to move the object. And that roughness is what's given by that coefficient of friction mu. So this mu basically determines what's the roughness between these two objects. How jaggedy is that surface, or how smoothly polished is that surface? So now I want to show you what we're going to be doing in our lab. So you're going to have a person riding on one of the scooters from our class, and another person is going to be pulling them along. And you guys are each going to hold the ends of a pair of spring scales. And I drew them as yellow because the spring scales we're going to be using are in fact yellow. The spring scales max out at 50 newtons, and it's going to take a little bit more than 50 newtons in a lot of your cases. Probably around 60 newtons, maybe at most about 80 newtons. More than that, perhaps if the wheels of your scooter are not so smooth. So you're going to be holding on to both of those scales, so it allows you to divide the force between the two. So if you've got one scale that's applying 30 newtons and the other one's applying 30 newtons, then you've got a total pulling force of 60 newtons. So that's why we're using both of those scales. So you're dividing that force out. Now let's do the free body diagram for this person on the scale here. So acting on this person, we've got the force due to gravity, of course, the weight of that person. And then supporting them is the force of the scooter. So the normal force is actually applied by the scooter in this case, which should be equal and opposite the force due to gravity. And then we've got the pulling force of our person. And then what we are going to do specifically here is pull with a force just big enough so that we're pulling with a constant speed. So if this object has to go at a constant speed, then is that force of friction that's acting against the force of the pull, should this be greater than, less than, or equal to the force of the pull? So we want you to be traveling along with a constant speed. If that's the case, should this force of friction be greater than, less than, or equal to the force of the pull? Well, it should be equal to, equal in size. So what you're going to find when you are looking at the measurements on your spring scales up here, when you look at that measurement, that's going to tell you the magnitude of the frictional force, spring scale, and also the magnitude of your pull. But the spring scale, so the spring scale is both of those values, but the pull is going to be in one direction and the friction is going to be in the opposite direction. And since we're looking at this, we should relate it back to a coordinate plane. So positive, positive, negative, negative. So I would define my pull as being positive and my friction as being negative. So what you're going to be doing in your lab is actually determining how much frictional force the scale, or how much frictional force is acting on you riding the scooter. Okay, so now the question is, how do we actually figure out what the coefficient of friction is? So the coefficient of friction is defined as the ratio of our frictional force to our normal force. So what you're going to have to do is figure out what the normal force needs to be acting on you and what the frictional force is acting on you based on the information from your spring scale, and then calculate your coefficient of friction. Then in our lab, what you guys are going to do is you're going to actually take all of that data from every person in your group, and you're going to graph it. And you're going to determine if the mass of a person has any effect on coefficient of friction. Is a heavier person going to result in a greater coefficient of friction? So that's going to be our overall question for this lab. If you have any questions about what you watched today, then try first just going back through, listening to it again, and if you're still confused, please let me know, and I will be more than happy to explain things perhaps in a different and more clear way. Thank you very much for watching.